Inside this laboratory near Oxford, England, there's a machine which every day Andy Kirk and his team transform into a star on Earth.
This machine is called a Tokamak. It's effectively a large magnetic bottle, a cage to hold a very hot plasma. We're able to recreate the conditions within a star.
Inside the Tokamak, hydrogen atoms naturally repel each other. To smash hydrogen atoms together, the Tokamak heats them to more than 166 million degrees. At these temperatures, the energized hydrogen atoms are moving so fast they can't avoid smashing into each other.
If you heat it up, heat is motion, and the motion of hot particles will be enough to overcome the repulsive force.
When everything goes right,
Starting shot.
the result is the single best power plant in the universe, nuclear fusion. Traveling at over 1,000 kilometers a second, the hydrogen atoms smash into each other and fuse, creating a new element, helium, and a small amount of pure energy.
The hydrogen gas weighs slightly more than the helium. You lost mass in the process of burning. That mass that you lost, the missing mass, turns into energy.
The Tokamak can only maintain fusion for a fraction of a second. But inside a real star, fusion continues for billions of years. The reason is simple: size.
The engine which drives a star is gravity. That's why stars are big. Stars are huge. You need that amount of gravity in order to compress the star to create fantastic amounts of heat sufficient to ignite nuclear fusion. That is the secret of the stars. That's why stars shine.
Fusion at the core of a star generates the explosive force of 1 billion nuclear bombs every second.
A star is a gigantic hydrogen bomb. So why doesn't it simply blow apart? It's because gravity is compressing the outer layers of the star.
Gravity and fusion are in an epic battle.
We have this constant tension between gravity, which wants to crush a star to
blasting a stream of electrical particles deep into space. This is the solar wind. It can damage spaceships and satellites, even put astronauts' lives in jeopardy. To discover how the magnetic loops trigger the solar wind, a team of scientists at Caltech recreate the surface of a star right here on Earth.
It's very exciting to be able to create in a laboratory the same sort of physics that are on the solar surface. We can't go there, we can't even send probes there, but we can try to study what's happening there.
An airless chamber simulates the vacuum of space. An enormous electric current produces a pair of man-made magnetic loops.
the main difference between the plasma loops we make in the lab and the ones on the surface of the sun is just their size. The ones we make in lab are, you know, about this big, and the ones on the surface of the sun can be many times the size of the Earth.
Their experiment reveals that when magnetic loops clash in the lab, they trigger a massive burst of energy. When giant loops collide on the surface of a star, the energy released sends temperatures soaring from 5,500 to 5.5 million degrees. That extreme heat triggers the solar wind, sending millions of tons of particles streaming out into space. The bigger the star, the more deadly the wind.
If we were orbiting a star like Eta Carinae at the same distance, it would be hell on Earth, quite literally. The amount of energy blasting down on the Earth would strip away our atmosphere, boil our oceans, melt the surface.
Understanding how stars work could help us protect ourselves by predicting their most destructive forces. But there's nothing we can do to protect ourselves when a star dies. In its final moments, it annihilates everything around it. From the moment of its birth, every star is destined to die. Its fuel will run out. Then gravity will win the battle with fusion, triggering a chain of events that will destroy the star.